on the bench we have a T-network antenna matcher. This is a homebrew project from several years ago. This matching unit is the main component of my multi-HF doublet. It's an antenna arrangement with this tuner that can operate comfortably from 160 meters through to 10 meters. I'm not sure we can go much higher than 10 meters. I've never tried it, but the inductor does seem to max out or minimum out around about the top couple of bands. But this turned out to be a very useful project. It's capable of tuning almost anything. It's a fairly standard tuner. It's the T-match. There's a schematic there. So you can see that the way we've set this up is on this side we've got the antenna load capacitance, and we've got a switch. We can switch into any number of 3 antennas. So typically we might have the multi-band doublet on say position 1, the multi-band sloper, primarily designed for 40 and 15 meters, but does tune up on most frequencies with this tuner. And position 3 is quite often a dummy load or even a ground. So that's that. And the tuning capacitors, quite high voltage. I don't know what their exact rating are, but it would be several kV. Their range is approximately 50 picofarads through to approximately 500 picofarads. So quite good range. Both the source and the load are the same. The source is the radio, and again we've got a switching arrangement here, so we can switch in a number of radios. Typically at the moment we're running the Kenwood TS930 in position 1 and a receiver in position 2. We do have other radios, but they're just normally not connected to this tuner. The inductor is a roughly a 0 to 19 microfarad roller inductor, and it's connected to a counter. So approximately counts 10 for each rotation. So that gives us great precision in being able to pick a precise inductor. Some of the impedances that we're trying to match can be quite high Q, so having the precision to get a matching dip sometimes can be fairly specific. So without the gear reduction of the inductor counter, it would be very difficult. Also, the capacitors have 6:1 ratio planetary reduction drives. So you'll notice the knob is rotating roughly 6 times the speed of the counter indicator. So again, it allows for great precision when setting the capacitors. I believe that the capacitors you could probably get away without having the reduction drives, but it is certainly a nice feature. Okay, so that's the front of the tuner and the a few basic controls. Just around, and no surprise, this is what the rear looks like. The 3 coax connectors for the 3 radio positions, the 3 antenna connectors for the three antenna positions. We've also got a bonding post there to put a good ground on this. Fairly important. Tuning around on these things, you can actually produce some quite high voltages, for interference with the equipment, and also, you know, you don't want to touch anything that's got a bit of high voltage RF on it. It's not comfortable. Okay, inside here we can see the capacitors. Now I'm just rotating the planetary drives there. You can see got fairly good precision. The planetary drives are fairly low profile and relatively cheap. They're nice and smooth as well, which is another great feature. The capacitors, if you look at the schematic, these are floating. So we've got these up on little insulator posts here. There's a fiberglass right here. So the capacitors sit above ground. The inductor, one end is grounded, the other end is connected to the capacitors. Again, if we look at the schematic, fairly straightforward. The switches are reasonably robust, quite good for reasonable voltages and currents. I wouldn't hot switch these at any power. I would tend not to hot switch these anyway. Also, the inductor would only set the inductor at low power. It's not a good idea to tune the inductor if you've got high RF, and the reason is that you can quite often have high currents on the inductor, and you can burn the contact. Now we'll just have a closer look inside. Tipping the tuner up on its side. Okay, you can see clearly the source capacitor and the meshing. So we've got good spaces between the plates. Like I say, it's probably good for a couple of kV. Don't know what this tuner would actually be rated to, but I generally run it at 100 watts, which is very comfortable. I suspect this is probably good for a kilowatt if you really pushed it, or somewhere around that figure. The roller inductor, see, larger spaces at the end to give again some more control over the lower inductance values that you needed for higher frequencies. As you can imagine, that's not a fantastic contact, which is why we don't use the roller inductors when transmitting. The other side laid out similar. Now the layout for this was done in a CAD program to try and get the ideal separation between the components so we don't get any interaction. Also to try and get a optimized layout for the front panel, and the assembly obviously is fairly critical. What else can we say? With most antenna matchers, tuners, there would be a balun for open wire. Now I've decided deliberately not to include the balun within the tuner, and the reason being is I wanted to experiment with a few balun designs, and so the balun was always going to be external. So obviously in one of the antenna positions it can go straight into a balun. It can be a 4-to-1 step up to twin feeder, or as we have it at the moment, it's low loss coax up out of the radio room onto to a stubby mast where we've got a 4-to-1 balun and choking balun. So they're actually remote from the radio room, and that's turned out to be probably the best arrangement. So again, no need to have the balun in the tuner. It makes a nice clean arrangement, and like I say, it's very flexible if you want to try different approaches out to matching HF antennas. Okay, I've also got some photographs from the construction phase of this project. This might be a bit interesting. I couldn't find an enclosure that was suitable, so it was fabricated out of some aluminium sheet, which turned out to be gone a bad way to tackle it. The general layout on the bottom sheet and the front panels assembled once all the main components are in place. So again, the layout with a CAD program, got everything positioned quite nicely, especially the front panel. So quite an enjoyable project. Okay, the basic tune-up procedure for the T-network antenna matcher is fairly standard. So we'll go to CW position. We're running at low power for a couple of reasons. One is not to cause interference to others. The other is that if we have very high SWR, we don't want to cause any issues there, so best to tune up as lower power as possible. So there we have quite a high SWR. Now, as far as the antenna matcher goes, the load should be set to near max. I won't quite put it on max. The source set to about halfway. Now this is the center of the capacitance on the source and the higher capacitance on the load side. And at this point we will tune the inductor to look for a dip. Yeah, we get a bit of a dip there, and then we increase the source, we'll decrease it, let's see if we can improve on the dip. Yeah, so we're sort of working the source capacitance and the inductor, looking for the best possible match, and that looks pretty good right there. So we've maintained a high load C. The source is on the 1 to 100 scale about 35, and the inductor on the counter is at 228. So we work our way through the bands, and we can just record, have a cheat sheet, so that whenever you want to move to a band, you just check the cheat sheet and you're on that band. Very easy. So it's not always in this tune-up procedure quite as easy. Sometimes the load capacitance need to be juggled as well. So we'll just see if we can find a band that's more problematic. We'll try perhaps I don't know, 15 meters. Again, we'll check. Yep, we've got a reasonably high SWR. The source is now set to about halfway, 50 on the dial, which roughly equates to half the capacitance. And now we just We'll bring the inductor down, so we're reducing the count number. It was also reducing the amount of inductance in the circuit. Comes down a fair way, and got a very small dip there. And okay, so now we're going to have to reduce the load C. Again, finding the ideal match sometimes not that straightforward, but there we go, we've made that fairly quickly. So the source actually stayed roughly around the middle. The load C is just below half, and the inductor counter is 108, which is getting close to the minimum inductance. We probably could not go much higher in frequency on this particular matching unit. So that's the tune-up procedure, which is actually fairly standard for most T-match tuners. And like I say, once you've established the matching parameters for any particular band, good idea to record it on a bit of a cheat sheet so that you can tune up quickly. But as you can see, even with that procedure, it's not that hard to match. Now, some of the frequencies are slightly high Q, particularly the lower bands, and so even moving within the band does require a bit of adjustment. But it does mean that you've got a pretty much a perfect match. So the transmitter is very happy. Alright, that's the overview for my homebrew T-network antenna matcher. Hope it was enjoyable, and thank you for watching.